My name is Kuang-Chih Lee. I'm the second author of this papers. Today I'm going to present the KDD workshop paper. The title is Optimal Reserve Price for Online Advertisement Trading Based on the Inventory Identification. So the authors are Hui, Kuang-Chih, and Liang. Those people right now they are working in Alibaba. Before they all work in Yahoo. So this paper is done when those people worked at Yahoo. Okay, so let's talk about the motivation of this paper. So we all know that digital advertisement market is about multi-billion business, and today it's kind of this business has been kind of fully developed into lots of kind of different business units. So the people would know that there would be supply side and demand side. There's also exchanges for the online kind of advertisement. And reserve price is very, very important, especially for the seller side revenue optimizations. And traditionally, what people usually do, especially like Yahoo or other companies, those reserve price typically is set based on human judgment. Basically, in Yahoo before, what we did is every week, the salespeople they get together, look at all the transaction price across different inventories, and they just use a technique. Look at all the report, and they use a technique we call eyeballing. Basically, just use eye, look at all the results, and manually decide the reserve price for different type of inventory. So this is a kind of a human work, and it's not guaranteed to be optimal for sure, and also it's not granular enough. Human cannot select say that cannot cannot separate the inventory into very different types. They can only like treat the inventory into certain amount, very small amount of combinations, say that by publishers and so on. They cannot look into very detailed features like different users, demographics, and so on to decide different price for different group of users. So we would like to present a dynamic reserve price algorithm based on the knowledge of the past transactions, and then and the last thing we want to emphasize here is that exchange revenue typically is very sensitive to those reserve price set up, because if you overprice, typically you will have a large opportunity cost loss, because a lot of buyer basically they bid below the reserve price and the transaction cannot be made. I would also like to emphasize here, this paper, the reserve price algorithm we present here is called the hard floor price, which means that we determine the reserve price before the auctions made it. And it's independent from the first bid price. There are also lots of algorithms today talk about as called soft reserve price. Those reserve price actually, either the reserve price determined after the transaction, after the people submitted the price, so they have dependency with the current first bid or second bid price. But we believe those mechanisms are not fair for the buyers, and also if buyers fund the exchange, they use the soft reserve price, they typically will start to shade their bid, because if they reduce their price, they typically will see they can observe that their transaction price will also be reduced, because the reserve price is kind of correlated with their bid price. So this is not what we want to do here. Okay, so the research backgrounds in this area, actually there are not many related work. So I only point two papers here which is kind of related to the reserve price. But I want to emphasize here those two papers, the first one, the second one, they are more theoretical. I mean, one paper is also my paper published last year, KDD. Basically, we look at all the distributions of the bid price and so on, try to build some distributions and try to maximize the revenues based on those distributions. We call the variations functions across all different buyers. So those algorithms typically can give good results. However, they cannot, look at lots of different features across different type of inventories. So that's one of the disadvantages for those type of theoretical paper if they want to calculate the bid densities. So the last one is actually a very old paper, more than 10 years ago, and this actually motivates our papers. So this is actually, it's not in the areas in the advertisement, it's actually a paper in the computer vision area. They want to detect human face through the images. They build a very fast algorithm called the Cascade boosting algorithms. And those algorithms can detect human face very quick in real time. So by adjust lots of different type of classifiers. So the question is, this paper we want to, the ideas of this paper, we want to build actually classifier to detect the high value inventories. And we also want to build another classifier to detect those inventories, the first price and the second price, they have huge gap. Okay, so the motivation here, why do we want to focus on the high value inventory? Because we noticed that most of the revenue actually come from those small portions of inventories. Typically, in our marketplace, more than 80% of the revenue actually come from those high value inventories. So if we can put accurate pricings on those high value inventory, actually our experiment shows that there is a significant impact to improve the revenues on the high value inventories. And there wouldn't be any impact for the rest, most of the inventories in the exchange side. And for this reason, most of the buyers, they won't notice on this change. And yeah, so that means I'm kind of talk about here. So that won't kind of interfere with lots of existing models, and buyers won't kind of notice all those things. Okay, so how it works? What we did here is we try to build two different type of classifiers. One is we want to detect high value inventories. The other one is we want to build another classifier to figure out those inventory, actually the first price and the second price, they have huge gap. Okay, those are the features we list that we use here. So we divide the feature types into three different scenarios: the publishers, and typically those related to the site information, like the top level domains, layout, ad size, and the SSP host and ad positions. And we also look at a huge amount of the user information. That kind of distinguish our paper with lots of previous papers. They talk about you to build the distributions of the variation functions or bid landscape, those type of approach. So we look at the age, genders, device type, geo informations, all those kind of very detailed informations from the user we collect. We also look at the buyer informations and like the group of buyers and so on. I also want to make a note here. In our marketplace, we are not allowed to discriminate any kind of buyers. So which means I cannot set a reserve price for given buyers. very high for one buyer and set low for other buyer. I cannot make any discriminations. So what we want to do is what we can do here is we need to group buyers into groups and set the reserve price not in very granular level to the each individual buyers. At least the reserve price at least to be more than 10 buyers. And we also look at all of day of the week. Those are the standard features people use on the buyer side to predict the bid price as well. Okay, so those are the features, correlated to the high values identifications. What we list here is the importance factors with each individual features that they're correlated to the price. So we can see that, and so the left-hand side with the high value identification, the right-hand side with those features, they have a high correlation with the price separations. So the boosting algorithms, kind of it's a standard ADA boost algorithm. So what we used to do is we want to build a set of classifiers. They look at the past of the training data. So X represent each individual inventories and their corresponding features. The Y would be the labels, which means that we kind of manually label the each inventories. If their transaction price larger than certain given amount, I cannot disclose what this amount is. Typically, we set it's several multiples of the average transaction price here, and as high value inventories. And we label them into two different classes. One is a high value inventory, another would be the low value inventories. What we try to do here for within this for loop, each time basically we try to train a classifiers and try to minimize all the errors. And once we finish that, we try to adjust the associated weight for each individual samples by those errors. And then after that, we normalize all the weights associated with each individual samples, and then we start the next round to select the second classifiers, which try to minimize this weighted data set until we find the final output of the classifiers. And after that, we actually build the cascade structures. Each individual node you can see here represent a boosting classifier I mentioned earlier. So what here we can do is try to make some trade-off between the false positive rate and the true positive rate. So in our scenario, basically what we want to do is that we want to have very low false positive rate, because if we made any mistake to put low value inventories into the high value inventory class, so in the runtime, typically bidder, they are smart, they submit a very low bid price, and you set a high reserve price for those inventory, you are going to lose money because the transaction is not going to be made. So we want to have very low false positive. However, the true positive side, we can kind of have some trade-off here. If we don't have very high true positive, that's probably okay, because it's just make something that we cannot detect the high value inventories. The reserve price is still based on the standard reserve price we set before. So at least we don't lose any revenue here. So what we want to make sure here is we try to build a set of cascade. Each individual knows they are boosting algorithms, and we play with the false positive and the false negative rate, and we want to make sure that after several classifiers concatenate together, we got a very low false positive rate. And we prove that for this scenario, if we concatenate 10 classifiers together, we will reduce the false positive rate into very small amount. that cannot be done by if you just want to train one single individual classifier. And we observe that that would introduce around like for this case it's about 8% revenue lift. And this is the Cascade algorithm we want to present here. I mean, I want to skip this because it's a little bit detailed, but this, as I said, a high level sense is basically we just want to make some trade-off between the false positive rate and the true positive rate basically. So each round when we pick up classifier, we want to make sure the false positive rate can be keep reduced, and we tolerate the true positive rate can also slightly become worse. Okay, those are the AUC we after we build those cascade classifiers. So left hand side is the one with the training data set, and the right hand side is the test data set. It's slightly decreased, but at least for the to detect high values classifier, this one is at least doing good job. And the next one, we will also build classifier to test if we can detect there is huge gap between the first and second price, and this classifier is not perform as well, does not perform as well as the previous one. Okay, and this is some kind of simulation results on the true auction data we have in Yahoo ad exchange, and we took like the 10% random samples, and we look at if we don't apply this cascade algorithm to determine the reserve price, and we got these revenues about the 116K. And after we apply this new algorithm to boost a certain reserve price for some inventories, we got around 125K revenues. And there are certain amount of the revenues they never got changed based on this adjustment. So the overall, when we calculate the revenue lift, it's about 3.5%. So it kind of a significant revenue lift. So the conclusion is that so for these problems, we want to build classifier to detect the high value inventory and then set up the reserve price associated with that. And we want to make a note on that. Basically, if you want to build a single classifier to do such things, it's very, very hard to do that. So that's why we choose cascade classifiers, and we made trade-off between the true positive and the false positive. And so this is about our talk. Is there any other questions?